Okay, so we're going to look at problem 734. And it says for the power hacksaw, which is up here at this instant in time, the 1 3/4 inch crank rotates clockwise at 70 RPM and decelerates at 45 radians per second squared. Use the relative acceleration method to graphically determine the linear velocity and of the saw blade as well as the linear acceleration. So let's look at what we know. So this is problem 734. Okay. So they're giving us the angular acceleration of link number 2, which is the crank, and that is 70 RPMs. And our angular acceleration of that same link is 45 radians per second squared. Now, this is going at a clockwise rotation. And because this is decelerating, this is going to rotate in the opposite direction acceleration wise because it's decelerating. Okay. So that's how we handle that. It wouldn't be a negative value. It is just going to be that it's going in the opposite direction of the actual motion itself. Okay. So kinematic diagram first. So kinematic diagram is going to look like this. And I'm going to confirm my numbers because I'm going to confirm the numbers. So I want to go from here to here. I drew this a while back, and that's why I want to confirm everything and make sure my distances are okay, because I don't want to get caught where it's not quite right. And then the other dimensions that I have are 2.5. Here to here. Oh, why would that be on? Oh, I'm at the wrong one. That's why. I'm down here from frame to slider, 2.5. Excellent. And I think that's it. Okay, so those should be good. So my diagram looks like it checks out. Now what we're going to do is we're going to put our line of actions, if you would, for each one of the elements. So I know that my slider is only going to go horizontal, and this is going to be my unknown because I want to find out what is the straight line velocity and the acceleration of my slider, which is going to be point C. So my velocity, I'm going to have to do the velocity first, of point C is going to be along this line of action. So I'm going to rename this as BC. Okay. This crank is going in a clockwise direction, so it's going this way. So I'm anticipating my velocity at C is going to be pointing to the right. Now, we know that everything about the crank as far as how fast it's rotating, so we'll be able to calculate the magnitude of B, and then we'll also know the direction perpendicular to link number 3 is going to be for the velocity of C relative to B. So let me put that direction in place, perpendicular. There we go. And that's going to be the velocity of C relative to B. And then my velocity of B. I'm going to put line of action on here right now, but we will be able to calculate its magnitude because we do know everything about link number 2. So let's calculate the magnitude of velocity of B. So I'm going to go back underneath here. I'm going to calculate the velocity of point B, because it's on the end point of the length that we know everything about. It's going to be W2 times the radius to point B. Now, W2, we can't put the 70 RPMs in here, so we have to convert this to radians per second. So W2 is equal to 70 revolutions per minute, okay? And you always have to, convert this. So 1 revolution, 2 pi radians, 1 minute, 60 seconds, right? So revolutions cancel, minute cancel. Our W2, do you know the number? Does anybody know the number? Josh, do you know that value? 7.33, okay. And that would be radians per second. Thank you. So that'll be the 7.33 radians per second. It's going to go there. And then the radius B was 1.75. Inches. Okay. So my velocity at B, what do we get for that? 3 times 1.75. Yep. So 12.83, and that's going to be inches per second. Okay. So that sets my length then of that vector. So I can draw this then. Now this was 1.75, 12. I'm going to do it 1-to-1 ratio because it's not going to be terribly big, I don't think. So 12.83. Oh, kind of big. I think I'm going to move it a decimal place now that I see that. Let's see. Here, we'll do 1.283. That looks a little bit easier to handle. So we'll trim this away. All right, so now we're ready to start our vector diagram. So let's write out the vector equation. I'll just do it right here in AutoCAD rather than back and forth. We're probably getting used to what this is supposed to be anyway. So we know that our unknown velocity of C is going to be equal to the velocity of B plus vectorially the velocity of C relative to B. Okay, so we're going to start with our origin. It doesn't have to be perfect. It just has to be a known or an obvious one. And I'm going to copy my velocity at B. It's going to start at my origin here. And I'm going to add the velocity of B relative to, I'm sorry, C relative to B to the endpoint here. Move. I know that the velocity of C is going to be vertical. And line of action there is going to be here to here. And let's scooch over here. So I can trim away these guys. And I'm going to then add my arrowheads. So since the velocity is C, is starting at my origin, its tail is going to be there. Its tip is going to be at the intersection created with C relative to B. I go back over here and we'll measure our values to be sure we get what we're supposed to. So linear velocity from here to here. And I'm going to ask, does your velocity of C look like this number here, or is it that number? Just gonna see if there's a confirmation. Yep, okay, perfect. And then let me just add the other ones here because I know I'm gonna need them later on. It's in a hurry. I'm not really in a hurry. I'm just trying to be efficient. And then things don't, I don't click the right buttons because I'm being a little bit too eager. Okay. And what I'm going to do now is I'm going to just write down those three values, but I'm going to put it to its actual numbers. So my velocity of B I have is 12.83. My velocity of C would be 9.541 inches per second. And my velocity of C relative to B is going to be 11.542 inches per second. So those I'm going to be referring back to. So if we look back at our problem, it wanted to know for number 34, determine the linear velocity of that saw blade. Our velocity at C is the linear velocity of that saw blade, okay? And it's going to the right, okay? So it's in that direction. So that's the first part of this problem, the linear velocity value, okay? Now we need to find out what is the acceleration, the straight line acceleration of that very same link. And we're going to use the relative acceleration equation for that. Now, we're going to use the same format. No, I didn't write it down in here, as we did for our relative velocity. So our relative velocity equation was the velocity of C is equal to the velocity of B plus factorially C relative to B. Okay, and we wrote that on the AutoCAD. So now that means that our relative acceleration is going to be the acceleration of C. It's going to be equal to the acceleration of B plus factorially the acceleration of C relative to B. Okay. Now looking at our motion here, the acceleration of C is that saw blade. It is a slider. It will not have a tangential or a normal component. So this is going to just be acceleration of C down here. Okay. The acceleration of B, we look back, B is on link number 2 and it is rotating around a fixed center. It will have a tangential and a normal. And then the same thing for our acceleration of C relative to B. That's going to have a normal and tangential as well. Back over here, we're going to expand each one of those out. The acceleration of B normal plus factorially the acceleration of B tangential plus factorially the acceleration of C relative to B normal plus factorially the acceleration of C relative to B tangential. Okay. Any questions so far? Does that make sense why certain ones have tangents and normals and other one, the one didn't, because it's a slider? Okay. All right, so starting over here on the left-hand side, our acceleration at C, because it's a slider, we know that it's going to be moving horizontally only, okay? We don't know its magnitude, so we can put a little circle here for magnitude. But direction, we know is going to be horizontal, so we can just go, we know what the direction is, okay? And that's good. We only have the one unknown on the left-hand side. Now we're going to cross over the equal sign, and we're going to look to our normal tangentials of the other 2 points. So the normal at B, again, we look back to our equation sheet. And if we look for the normal component to calculate it, we can use either one of these equations. Because point B is on link number 2, and we know all of these, either one of these is going to be fine, okay? So we know we can calculate the magnitude, and then the direction is going to go from point B and point towards the center of rotation, so right along that link. So since we're here, we're going to say the normal component at B is going to be equal to the velocity of B squared. I'm just picking one of them. You can pick the other one. You're going to get the same answer, and the radius to B. So we know that the magnitude of the velocity at B was right up here, 12.83 inches per second, So 12.83 inches per second, and then we're going to square that full value and units divided by the radius or the length of link number 2, which is 1.75 inches. This is going to square and square, so it gets rid of that one, gets rid of that one. So we're going to be in inches per second squared. So 12.83. I'm getting 94.0622. Just want to get a confirmation on that, make sure. Bye, Chris. Have a good night. Yes, thank you, Josh. Then, so that means that we've got our magnitude and direction for that one. So we'll be looking there. Tangential at B. Tangential at B is going to be the radius times the angular acceleration. Angular acceleration of link number 2 was given to us, and we know its distance to its radius. So we can calculate the magnitude. The direction is going to be perpendicular to that link. So we know direction as well. So down a little bit here. A, B tangential is going to be the radius to B times the angular acceleration of link number 2. Now, the direction will come into play with the deceleration, okay? But here, we're just going to use its magnitude. So this is going to equal 1.75 inches times 45 radians per second squared. So 45 times 1.75, it's going to be 78.75 inches per second squared. And just looking for one more confirmation. Awesome. Okay. Now we're going to look to our normal component of C relative to B. So the normal component of C relative to B magnitude wise. Here's the equation. We don't know angular acceleration of link number 3. So we do know the velocity of C relative to B. So that's going to be the value up there. So we can calculate its magnitude. And then its direction is going to point from C towards B along the link. Okay, along the link. So this is going to be C relative to B normal. And this is going to be the velocity of C relative to B divided by the radius of C relative to B. Okay. And this has to be squared. Don't forget to square that. Now up here on our velocity vector, diagram, we measured C relative to B. So this is our value. It'll be 11.542 inches per second. We're going to square that entire value divided by the length of link number 3, which is 6 inches. So this is going to square, get rid of one of those, rid of that one. So 11.542 squared. I'm getting 22.203 inches per second squared. Okay, cool. All right. Now we're going to look to our tangential. The tangential component of C relative to B, to calculate it, we would need the angular acceleration of that link. We do not have it. Okay, so that means magnitude wise, we don't know, but direction is going to be perpendicular to link number 3. Okay, so now we have anything that we know magnitude wise calculated, and then we have identified anything that we don't know, and they are separated by the equal sign. So we are ready to do our vector equation. So we're going to go back to our CAD, and I'm looking at these numbers, 94. Yeah, we're definitely going to have to move our decimal place again. So I am going to grab the same origin just because it's done already. And I'm going to move that like up here, and we might have to move it around. And I'm going to grab this vector equation here, and we're just going to write it like over here. Okay, I know I'm going to have to get longer, but I'm going to add it here so I don't have to keep flipping back. So I have the acceleration of C. It's going to be equal to the acceleration normal at B plus vectorially the acceleration tangential at B plus vectorially the acceleration normal at C relative to B plus vectorially the acceleration tangential C relative to B. There we go. Okay, so then at least we have that out here. This. Okay. So we're going to start on the right-hand side here because the normal component of B is where we know the most information. So we are going to copy the line of action, which is going to be the link itself, because the velocity, I'm sorry, the acceleration of that normal component at B is going to point from B towards A. So we're going to change this to a color. We'll call that, we'll do the resultant. That's fine for the B's. And because we're going to scale this, this is going to be, I'm going to say 9.4 inches, I guess. So 9.4, and I'm going to do 0.622. Okay. So we'll have to move. I'll maybe go over here. Right there. And we'll extend this there. Okay. Resultant. Oh, that's kind of big. Um, uh, that way, once I get one done, then it's just a copy for the other ones. Normal. Okay, so that's my normal component. Now on the end point of that, I am going to add the line of action and the for the tangential. Actually, I know magnitude and it's going to be perpendicular to this. So I am going to grab the line of action of the velocity at B, and I'm going to put that on the endpoint. Now, this is where we have to determine which direction it's going in. Now, remember that the velocity, the angular velocity of link number 2 was going clockwise. We're decelerating, so that means it's going in the opposite direction for acceleration. So our acceleration tangential component is going to point up and to the left. So I'm going to move this so that it goes from here and it's going to go up, okay? And its magnitude was 78.75. So that means that, change this to resultant, that is going to be 7.875. 7.875 is the radius. So extend to here. And this will be the tangential component. Yeah. And then the arrowheads. Here we go. Okay, does everybody understand that direction? Makes sense? Okay. All right, so now on the endpoint there, we're going to add the normal of C relative to B. The normal of C relative to B is going to be along link number 3, so that's its line of action. It's going to point from C towards B. So it goes from the unknown to the known. So I'm going to copy that line of action for that link, and I know it's going to go from C towards B. And its length is 22.2. So that means that its radius is going to be 2.2203. There we go. So it's a shorter one, but it's not as tiny as some of those other ones. And we can get rid of this. And this is going to point down and to the right. Oh, from C towards B. Okay. And this is going to, oh, wait. Oh, this is the tangential. I'm sorry, I totally messed that up. And that would be B. And then this one is going to be the normal of C relative to B. Normal, Kelly, not tangential. There we go. I think I got that right. All right, so then we're on our last vector on the right-hand side. So this is going to be the tangential of C relative to B. So that's going to be along this line of action here, perpendicular to. So I'm just going to take this, it's going to be the same line of action, if you would, as our tangential. Now, we don't know its magnitude, and I really don't know which way it's pointing, okay? So we're just going to leave it kind of hanging out there, okay? So I'm going to copy this one. And this is going to be the tangential. Oh, okay. Good. Good, good, good. That's okay. We'll finish it up here and let's make sure that you get the correct answer. Or did you already figure out that you did? I'll finish it up here so that we've got it on record. So now that takes care of my right-hand side of my equation. I'm going to cross over and go to my left-hand side. You'll notice that C is on a straight horizontal line. So that's the that's going to be the path or the line of action for the acceleration of C. So I'm going to put it through the endpoint there. And then now we've got to find an intersection between the last vector, oopsie, the last vector that we drew, which was the tangent of C relative to B, and here. So it looks like they're going to intersect over here. So I'm gonna do an extend. I just had to draw that line as something that it could go to. And then I can extend this one down. And now that's where they're going to intersect. So I'm gonna trim this part away and that part away. So the tangential is down here. And since this is the intersection, that means that its arrowhead is going to be going down and to the leftish, right? That's going to be that one. And then the velocity or the acceleration of C and it's just going to be a straight line acceleration. It's not going to be a normal, okay? It's just going to be, or a normal or a tangential. It's a straight line velocity. So it is just going to be along or straight line acceleration because it's a slider along that direction. So now this is my final answer. So again, the moment of truth. I'm going to do my linear value here. And now it says 10.37. So that is actually 103. This would be the acceleration of C would be measured at 103.73 inches per second squared. And it is going to the left. Okay, it's decelerating, which makes sense. It makes sense because remember, our straight line velocity, it was pulling this way. So it was going to the right. So our straight line velocity going to the right. But because this is slowing down, crank 2 or link number 2 is slowing down, it's decelerating. Notice that even though we're a straight line acceleration, it's going in the opposite direction of motion because it's slowing down. So, oh my gosh, all makes sense. Now, I just got to make sure that my value matches. Oh my goodness, look at exactly matches number 34. Look at that. So yeah, that we are in good shape there. So let me go back over here and just review the items that you need to take screenshots of. You need to have a screenshot of your vector diagram with all your labels. I'm sorry, your kinematic diagram with all your labels, vector diagram with all your labels, and then your acceleration diagram with all the labels. Okay, and make sure that everything is viewable, the size of the text and such. Then, as far as hand calculations, anything that we had to write out. So when we go back over here, you know, calculating the velocity or the magnitude of the velocity of B, the measured values here, writing out your acceleration equation and any manual calculations that you got. And then I, on the back side here, put a box around my final answer for the acceleration of C and the direction that it was going in. So that's what you would need to hand in to get full credit for that problem. So any questions as we're here at the end? All right, I'm going to stop the recording